Okay, let's talk about some more logarithmic functions. So mostly we're talking about graphs today and the attributes of graphs of or logarithms. So what I need you to know is that logs are inverses of exponentials. Okay, the log and an exponential are inverse operations. They're inverse functions. Okay, so a log, yesterday we talked about log of a base of x, and we could rearrange the furniture, right, and get a similar type of equation. Log equals the base raised to the power, right? So this is our log equation, and this is your exponential, right, function. So what's true is that the base of your log translates to be the base of your exponential. Okay, so we can rewrite them as equivalent equations, and we can evaluate logs using this property. So it's important to understand that logs are inverses. Remember, inverse has that notation of -1. Okay, so a log is an inverse of an exponential. So when you see this notation, you need to think inverse. Logs and exponentials are inverses of each other. Okay, so here's some things about logs that you should know about. Right, they're not too much and not too bad. So let's practice writing some limit statements for this particular graph. Okay, so this is a graph of a positive log. Okay, we know it's a positive. Well, hopefully you'll learn that this is a positive log graph. Log, we don't know what the base is of x, right? So this will be a positive log graph. So as x approaches 0 from the right, means that we are coming this way towards our 0. And in what direction does your graph go? Your graph goes down. So whenever our graph goes down, the arrow goes down, our infinity sign is negative infinity. Okay, we'll never actually get to 0 because there's that vertical asymptote through 0. So we can never take the log of a negative. This number here will always be a positive value. Okay, because you can't take the log of a negative. Your calculator won't let you. The logs are not defined for negative values of x. But for the right side, what direction does your arrow go on the right side? So the right is still as x approaches positive infinity. Okay, so that's going over to the right side. Our arrow is pointing up, which means our limit goes to positive infinity. Okay, so if the graph goes down, that goes to negative infinity, and if the graph goes up, the limit is positive infinity. So let's look at our next graph. Okay, we're going to learn that this is a negative log graph. Right? This negative here is an x-axis reflection. Okay, this is an x-axis reflection. So where our positive log graph looks like this, the negative log graph is a reflection over the x-axis. Okay, so still we're looking at the limit as x approaches 0 from the right. That's still your left end behavior, your left limit statement. This graph still won't cross 0. And what direction does our arrow point as you go towards 0? The arrow points up, which means our limit is positive infinity. Okay, if the arrow goes up, it's to positive infinity. And our right limit statement, lim as x approaches positive infinity. I know it's kind of hard to see, but what direction does your arrow go for this graph? Right, it goes down. It will always go down, but it will go down very, very little. But it will still go down. Eventually, we'll get to negative, very large values. So the limit is going to be negative infinity. So letter C. Notice there's not a graph for letter C. So they're expecting you to understand some things about this function. So is our graph a positive log function or a negative log function? This is a positive log function. In other words, the n behaviors will be the same as the other positive log function that we've seen, which was example A, right? Example A is the graph of a positive log function. So our limit statements are going to be the exact same as the graph for A. So these ones are asking you about concavity and whether our function is increasing or decreasing. Okay, remember, increasing or decreasing is all about the y values. Are the y values getting larger or are the y values getting smaller as x's get larger, right? So x always goes from 0 to infinity. What's happening to the y's? So on part A, what's happening to our y values? They're getting smaller. So this is a decreasing y values, right? The y value gets less and less and less as x gets larger and larger. And this graph is concave what direction? Concave up. Okay, how about these y values? These ones are increasing. Your y values are getting larger as x gets larger. But this concavity is concave down. Okay, so remember, this is a positive log graph. Positive log. This is a negative log graph. Right? Because generalities are what math is made to do, right? We want to be able to predict what's going to happen when we don't have a graph. So looking at number 4, what's the positivity of our log graph? This is a negative log graph. So it's going to have the same concavity as all negative log graphs are going to have, which was the same as example A. Right? Example A was our negative log graph. So the y values are always decreasing, and this is concave up. So let's put this all together with our attributes. The x-intercept is always, unless there's a multiplier, at 1, 0. Okay, because anything to the 0 power equals 1. Right, so if the base of your log is the same as the base of your exponent, then anything to the 0 power is 1. So that's where it crosses your x-axis. Okay, and we always have that asymptote through your y-axis, which is the line x equals 0. Okay, so we always have a vertical asymptote through the origin along your y-axis. Okay, the domain is everything bigger than 0. The log will never be 0. So our domain is parentheses 0 to infinity, right? Not bracket, because we're never going to actually reach 0. So we have a 0 to infinity domain. And the range is all real values. In other words, minus infinity to positive infinity. So the range of your logarithm will always be all real numbers, no matter what happens to your function, whether it opens right or left, whether it's a reflection or whatever, you're always going to have all real values for your range. But the domain will change if we have a horizontal transformation. So if our graph gets moved to the right or to the left, then your asymptote gets moved to the right or to the left. And therefore your domain has been adjusted if your graph gets moved to the right or to the left. So what does that look like for a graph, or rather a log function? So has this function, 2 log base 3 of x, been moved any direction? Right, hopefully you know that it has not been moved anywhere, so the domain does not change, 0 to infinity, and the range is still all real values. Okay, so let's talk about what that looks like. We have A is your, well, okay, we'll go back before that. No, we'll stay there. So A times the log base of x minus c plus d. Okay, so these are the 4 places that we always see transformations. Okay, we always see transformations in these 4 places. So A, this is your vertical dilation. Okay, that's a vertical dilation. B is, of course, your base. That tells you how fast it's growing or how slow it's growing. The C, this is where your horizontal translation comes from. And of course, parentheses always tell you the opposite. So if it's a minus, it moves to the right, and if it's a plus, it moves to the left. And then our last one here must be your vertical shifting. Right, this is your vertical shift. So the only time that your domain will change is when we have parentheses. This is what we're looking for a domain restriction. Okay, so what we do to restrict our domain is you take whatever that parenthesis is, and it must be positive. Okay, we cannot have a negative. We cannot take the log of a negative number. So whatever is in parentheses, you set that greater than 0. It cannot be negative. Right? And then you solve and we figure out what it's got to be. So here on example 2, right, this has 3 transformations. There's a reflection, there is a dilation, and there is a horizontal. Right? So this is our horizontal transformation. So our domain is going to change. So we take that x minus 3 in parentheses, and we set it greater than 0. X must be a positive value, not equal to 0, greater than 0. So x has to be greater than 3. In order for this to be a positive number, I have to pick x values bigger than 3. So my domain is from 3 to infinity. Right? Those are all the numbers that are bigger than 3. And my range is the same as my range always is. There's no change to the range for a horizontal transformation. Okay, so this one has a couple of changes also. Number 1, it has a dilation, a vertical dilation, right? And it also has a horizontal dilation. If something is being multiplied by the x term, that's a horizontal dilation. But the whole entire thing together is your whole entire translation. So we set the entire equation 2x plus 3 bigger than 0. Whatever we are taking the log of must be a positive number. So we have to restrict anything that makes our log negative. So 2x has to be greater than negative 3. X has to be greater than negative 3/2. Okay, or if you want, negative 1.5 as a decimal, if that's what you're into. Okay, so our domain is from negative 3/2 to infinity. As long as my x value is bigger than negative 1.5, I will have a positive log to take. And then the range is no change in the range. So the last thing we need to know is stuff about tables. So what do we notice about a table? So we have x values and we have y values in our table. Okay, so let me draw myself a table. How do we know when we have an exponential growth function versus a logarithmic growth function? So here's an example of an exponential growth function. Exponential, it's missing an N. We are going to have a constant addition problem between your x values. Okay, so notice this is a constant addition, plus 2, plus 2, plus 2, plus 2. Okay, so constant, they're evenly spaced. Your x values are evenly spaced. But your y values, if we're going to have an exponential function, are going to have a multiplicative factor. So this is times 3, times 3, times 3. So for an exponential, your outputs have a multiplier and your inputs have an adder or subtractor, right? You can be getting minusing also. Now, what do we know about its inverse? So if that was an exponential, what's the inverse of an exponential? Oh, geez. A logarithm. So for logarithms, if they're inverses, that means the y's become the x's. So the x's have a multiplier, multiplying factor. And the y values have a addition factor. So that's how you can tell if a table of values exhibits exponential growth or logarithmic growth based upon which one is being multiplied. For exponentials, the y's have multipliers. For logarithmics, the x's have multipliers. Okay, that sounds like a lot of stuff. Good luck to you on all of these types of problems.